Oh, hey, Samson. How are you? Yeah, a lot of my friends are really enjoying the game. All right, so we're going to use Matlab today. And so if you want to have it open, we're going to lecture probably the first 30, 40 minutes, but then after that, we'll be using Matlab. So if you want to use the computers here, you can go ahead and bring them. Okay, it's 5:30, so let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Sorry.
Tired? I hear you. It's that time of the semester already. Okay, hanging in there. That's good. You know, that's all we can do, right? Just hang in there the best that we can. Okay. So today is a MATLAB day, and so if you're just joining us on the Zoom call, then I do plan to do a MATLAB activity. In fact, I posted a starter code for you on Canvas as well. And so we're going to go through that in the second half of the class, but I do have some stuff I want to lecture on first. And so we're going to do that. That's the plan for today. Okay. Okay. Other announcements. So I graded the first homework. So homework 1 should be graded. And so you should see your grade on Canvas. You know, because this is an elective class, I grade the homeworks mostly on completion. And so I didn't leave that many comments unless I saw something that, you know, that really stood out to me on your homeworks. But if you want some additional feedback, then you can let me know. I've also posted the solutions for both the written responses and the code on Canvas as well. And then later I'll show you where you can find that stuff. Usually I post the solutions on the weekly page on the week that I graded in. Or you can just search for it in the files as well. And that's good there. All right, and so I think that's all my announcements. So are there any questions I can answer before we get started? Okay, all right, so let's go ahead and pick up where we left off. And so we left off last time talking about boundary conditions, right? And so we're kind of in the middle of solving the 2D diffusion equation using finite differences, right? And so we've learned how to apply the finite difference equation to our diffusion equation. And so the next step, and you know, the next step that we have to take before we can solve is to apply the boundary conditions. Okay. And I think the last thing that I said was that you know, just to kind of keep things simple for us, you know, mostly with the coding, just to make the coding simple, I'm going to assume that on each side of our domain, basically on each side of the square, we're going to have the same boundary condition, right? And so everything on the west side of the square is going to have the same boundary condition. Everything on the north side of the square is going to have the same boundary condition. Everything on the east side, same boundary condition, and everything on the south side, same boundary condition. So we only have 4 boundary conditions that we're going to need to worry about. Okay. The other thing that I didn't mention last time is that one thing that's really different about 2D problems is that we're going to apply boundary conditions on a lot of different nodes, right? Because if you think of our 1D case, right? Our 1D case, we had just a simple line, right? When we applied the boundary conditions, it was only on 2 of the nodes, right? So we only applied boundary conditions on the first node and on the last node, right? And so conceptually, it was very easy for us to do because, you know, we only knew that we only had one node that we have to apply our boundary condition on. For 2D, it's a lot different because we can have, you know, we can have so many nodes here resting on this edge, right? And each of these nodes is going to have a boundary condition. Okay. Same thing on the bottom. And depending on your grid spacing, you know, you can have anywhere between, you know, a few nodes, maybe like 3 or 4 nodes on an edge, to anywhere between hundreds, thousands. And so that's going to fundamentally change the way that we implement it. That we'll talk about later. Okay. But as a sneak preview, you know, what you'll see is that we're going to use a separate loop to assign our boundary conditions. Okay. All right. So let's go ahead and talk about the 2 types of boundary conditions that we can specify. Okay. So they're the same as our 1D case, but you know, I think it's useful to remember them. And so the first type of boundary condition, remember, is a Dirichlet type boundary condition. Okay. And so remember, the idea with Dirichlet is that we are directly specifying the value of the solution. Okay. And so in other words, we're going to say that phi on the boundary is equal to some specified phi naught. Okay. And so the good thing about Dirichlet boundary conditions is that the way that we implement them, the way that we mathematically, you know, implement them in the matrix is going to be kind of more or less exactly the same. Okay. So Dirichlet is pretty simple. Okay. So Neumann boundary conditions, on the other hand, is a is a condition or a specification of the solution derivative. Okay. And the interpretation of this one's going to change a little bit because we're in 2D space, right? And so the way that we're going to interpret this is we're going to say that we're going to take the derivative of phi with respect to n here, okay? And it's going to have some specified value, okay? Where this n right here, it can be either x or y, but the n here stands for normal, okay? And by normal, I mean the normal direction. And so whatever boundary that we're on, we're going to take the derivative in the direction normal to that surface or perpendicular to that surface, okay? Right, and so that's going to be important later when we actually go to implement it. Okay. All right, and so the next thing that we'll talk about is, identifying the boundary nodes, or how do we find where all the boundary nodes are? If you remember from Monday, we spent most of Monday talking about the ID scheme of our 2D finite difference, right? And so in other words, another way to say this is, how can we obtain the ID numbers for all the nodes on an edge? Okay. Right, because those ID numbers are going to be what we use to assign them to our matrix. Okay. And so the way we do this is we use the same IJ notation that we did for the interior nodes, except now when we know that we're on a boundary, either the I coordinate or the J coordinate is going to be fixed. Okay. Okay. And so what do I mean by that? So let's take one of the boundaries as an example. Okay, so let's do the west boundary. Okay. All right, so let me go ahead and draw just a mini square here. Okay. Let me draw some grid points on here. Not too many though. Okay, and so we know how the IJ coordinates work, and so we know the origin is down here, and so this has coordinates of 1, 1, right? An I coordinate of 1, J coordinate of 1. Right? And if we want to find the IJ coordinates for everything on the left boundary, we know some information right here, right? And so on the left boundary, we know that the J values are going to vary between 1 and Y. Okay. Right. Right. We know that because our left boundary is just going vertically up, right? And so to go vertically up on a line in our domain, that means our J has to go from 1 to ny. Okay. Okay. The thing that's fixed on our left boundary is the I coordinate, right? And so if you notice for everything on this left boundary, and so we'll say this is 1, 2, 1, 3, 1, 4, 1, 5, okay, and 1, 6. Okay. And so for all these nodes here, the I value is fixed, right? So the I coordinate is fixed at 1 for everything on the left boundary. Okay. That means when we're assigning boundary conditions for the left boundary, we only need to loop on the j because I is going to be fixed. Okay. Okay. Right, so all the boundaries kind of share this property. And so all the boundaries, depending on if it's, on what direction it is, one of the coordinates is going to be fixed, and then the other one we're going to loop over, okay? And if we know the ij coordinates, we can use our ID formula to get the ID, okay? Okay. Right, and you'll see this in action. You'll see this in action later. All right, any questions on this? And kind of the logic behind that? Okay. Okay, so that's the left boundary. I'm not going to redraw it again for each one, but I'll give you what the coordinates are. Okay. So for the right boundary, again, it's a vertical face, and so we're going to have to loop j, excuse me, between 1 and ny. Okay. Okay. And I here is going to be fixed, because it's a vertical face. But instead of being fixed at I is equal to 1, it's going to be fixed at nx, where nx is the number of nodes in that direction. Okay. And so to visit all the nodes on the right boundary, we write a for loop to visit all the j entries from 1 to ny, but we keep the I index fixed. Okay. Okay. Next, we have the top boundary. And so since the top boundary is a horizontal one, then we know we're going to loop I from 1 to nx. Okay. And then j here is going to be fixed at ny. Right, and then just for completeness, we have the bottom boundary. And so the bottom boundary, again, is a horizontal one. Okay, and so we're going to loop I from 1 to nx. And then j here is going to be fixed, but it's going to be fixed at the bottom. And so the fixed value for j is going to be 1. Okay. All right. And so now that we know how to visit each of the, or what the coordinates of each of the boundary nodes are, let me show you an example of a loop that you can use to visit all of them, okay? And let's say we're going to visit all the nodes on the right boundary. Okay. All right, and so for this, let's say that we defined a variable, and so let's say that nx is equal to, let's say we just have 10 nodes in each direction, okay? And so nx is equal to 10, and y is equal to 10, okay? Okay. And so to visit everything on the right boundary, we're going to write a for loop, okay? And so we're going to say for, okay? We know that we're looping on j. Okay. And so we're going to say for j. And since j is going to vary between 1 and ny, I'm going to say 1 : ny. Okay. And so this part of the code here makes sure that we visit or we loop over every single possible j value. Okay. Right. The next line in the code that we're going to write is we're going to compute the ID. Okay. And so I'm going to make a new variable called my ID. Right. And so this is going to compute the ID number. And then for this one, we're going to use the ID number formula that we talked about last time. Okay. And so remember, our ID number formula is j minus 1 times nx plus I. Okay. Right. And so given a generic ij coordinate, we would use this formula here to compute its ID number. Okay. The only thing is that for this particular loop, we know that we're visiting everything on the right boundary, right? And so what do we know about the right boundary? The right boundary has a fixed value of I, which is nx, okay? And so instead of I right here, we can just go ahead and plug in nx, because that's what we know is the values of the i's in that on that boundary. Okay. And so our ID formula now is my ID is equal to j minus 1 times nx plus nx, okay? Where we've substituted nx in for I, because we know that every node on the right boundary is going to have a I value of nx. Okay. Right, and so now that we compute the the ID number for every node on that every node on that boundary, or we're going to visit every single one, we can do some stuff with it. And so for now, I'll just say more code because we're going to work with it later on when we actually pull up Matlab. But I just wanted to show you an example of how to write a loop to visit every node on a boundary. Okay. All right. Any questions on this?
You wouldn't need to do a dot matrix or a dot
product?
Not a dot product, but
oh, dot multiply. Yeah. So for these ones, these are all just plain numbers, and so j, remember, is just a plain number because it's their loop index. Nx is just a plain number because it's just the number of nodes in that direction. So yeah, we don't need to do any matrix or element by element operations here. Actually, for none of the algorithms we're going to do in this class, we're never going to use dot times or dot divide or dot exponent or something like that. And so these algorithms are actually programmed to work with more basic programming languages. So because this feature in MATLAB where you do the dot before multiply, that's strictly a MATLAB thing. And so most programming languages actually don't have that. And so a lot of these methods, they're meant to work with like C++ or Fortran or Python. They don't rely on those operations. Okay. Any other questions on this example here? Okay. All right. So let's talk about how we actually apply our boundary conditions. Okay. And so the code, this kind of the pseudo code that we're going to write here would go into this area right here. Okay. And so after you computed the ID number for that boundary node, this is kind of the code that you would write to actually apply the boundary condition. Okay? Okay. All right, so let's start with Dirichlet. Okay. All right, so we know with Dirichlet, we directly apply the solution value. Okay, and so if you remember how we did that in the 1D case, what we did was we put a 1 on the diagonal entry of the left-hand side matrix. Okay, and so we're going to do the exact same thing here in 2D. Okay. And then the other thing that we did was we put the specified Dirichlet value into the right-hand side vector. Okay. And so just as a refresher, let's say that we have a boundary condition which says that the 7th index, so we'll say phi7, has a Dirichlet value of 17. Okay. And so the way that we would implement this in the matrix, we go down to the seventh row in the matrix. Okay. So this is the row for phi7 right here. Okay. We put a 1 on the diagonal. Okay. Where all the other entries in that row are 0. Okay. So this would be in the 7th column. Okay. 7th row, 7th column, we put a 1. And then in the 7th row, we put the applied Dirichlet value there, which is 17. Okay. Okay. All right, and so let's see how to actually apply this, using this my ID up here. Okay. And so if we assume that we've computed the ID number for this boundary node, then the way that we would apply it was that we would say the left-hand side matrix. Okay. And we need to obtain the diagonal entry. So this would be like my ID, comma, my ID. Okay. This is going to equal to 1. Okay. And so we're basically setting this guy right here. Okay. By a similar token, on the same row in the right-hand side vector, we're going to put our specified Dirichlet value, which in this case is 17. Okay. All right, so Dirichlet boundary condition is very simple. So after you compute the ID number, then you just make the diagonal entry 1, and you move the specified Dirichlet value to the right. Okay, so literally just two lines of code. All right. Any questions on this? Okay. All right, so Dirichlet is pretty straightforward. Now let's go over Neumann. Okay. All right, question, what's supposed to be my underscore ID? Oh, yeah. So I think up here I defined it as, yeah. So it should be my underscore ID. Yeah, thank you. Yeah, so you want to make sure that they match. Either one is fine, so you can use the underscore or not, just make sure that they match in both parts of your code. Okay. All right, so now let's talk about Neumann boundary conditions. So remember, Neumann boundary conditions for 2D cases, we're going to take the derivative in the normal direction. Okay. And what I mean by that is in the direction of the that is perpendicular to your side. Okay. And so for for 2D, a better or a more specific expression for this looks something like this. Okay. And so we're going to take the difference between the inner node minus the boundary node, and then we're going to divide that by alpha. Okay. And then we're going to set this equal to our Neumann boundary condition. Okay. Where this inner, what this is the immediate neighbor towards the interior of the domain. Okay. Okay. And so what do I mean by that? And so let me give you two examples here. So let me draw a vertical face example. Okay. Okay. And so let's say that we have just a chunk of our domain like this. Okay. And so if this is the boundary node that we're interested in, okay, and this face here is vertical, right? And so this is on kind of a broader kind of vertical face. That means the direction that's perpendicular to this is in the x direction, okay? And so what we're going to do is we're going to look for the neighbor that's immediately interior to this, immediately to the x direction, and that's going to be this guy right here, okay? And so this right here is phi inner, okay? And so we're going to take the difference between those two nodes and then set that equal to our Neumann boundary condition. Okay? And of course, you're going to have to find the ID number for that inner node as well. And so you're going to have to know how to do that. Okay. Same thing for a horizontal face. Okay. Right. And so let's say that we're on the bottom boundary. So the boundary is like this. Okay. So this right here is phi boundary. Since this is a horizontal face, then the direction that's perpendicular to this is the y direction. Okay. And so this is going to be phi inner right here. Okay. Oh, question? Oh, okay. I thought I heard something. I'm hearing what just up to. Okay. And so the thing that's unique about Neumann boundary conditions is that you're going to need to compute two ID numbers. Okay. The first one, of course, is going to be the boundary node. Okay. And the other ID number that you're going to need to compute is the one for the inner neighbor. Okay. Okay. And so I'm going to give you kind of an example code segment here. Okay. And I think this is the last thing before the example. Yes. Okay. Right. And so as an example, this would be kind of on the interior of the loop. And so, imagine this is on the interior of a loop. Okay. So this is inside a loop. Okay. And in particular, I think this is going to be a loop that visits the boundary nodes for a left boundary. Okay. Right. So remember, for a left boundary, the fixed number that we have here is I. Okay, and so the fixed I here is going to be 1. Okay. All right. So first, let's compute my ID. Okay. Where my ID is the ID number of the boundary node. Okay. Okay. And so that's going to be the same as before. And so we take j minus 1, we multiply by nx, and we add our fixed value of I, which is 1. Okay. Okay. Then we need to compute the ID number for the inner node, right? And so remember, the inner node, it still has the same j value, right? Because for the left boundary, the direction that's perpendicular to that is the x direction. And so if we're moving purely in the x direction, then our j coordinates can be the same. And if we're on the left boundary, then the direction that we're going to move to go inwards is to the right, right? And so we need the I coordinate for the node that's immediately to the right of this one, where if this one has an I number of 1, that means the one immediately to the right of it is going to have an I number of 2, okay? And so those are the two ID numbers that we're going to have. Okay. Now you're going to set the coefficient for the diagonal entry, okay? right? And so the coefficient, if we go back up to our finite difference approximation for this Neumann boundary condition, we can see here that the coefficient here is a -1, right? Next, we're going to set the coefficient for the inner neighbor, okay? And so that's going to be left-hand side matrix. We're still going to be in the myID row, but we're just going to move to a different column. Okay, so that's we have myID, comma, inner ID. And you can see here from this expression that the coefficient for phi inner is 1. Okay, so we're going to put a 1 right here. Okay. Right. And so, and then on the right-hand side, you're going to put the actual value of the boundary condition, where we're going to assume the value of the Neumann boundary condition is gamma. Okay, and then we need to multiply it by the grid spacing because we used a finite difference here. Okay, and so we basically took this denominator and multiplied it on both sides, such that the final equation that we're working with is minus phi boundary plus phi inner is equal to gamma times delta. Okay. And so this is the equation that we basically applied here. All right. Any questions on how we applied that?
And for the left-hand matrix equals a -1, where'd you get the -1 again?
Yeah, so the -1 comes from this one, right? Because we're basically applying this algebraic equation here, and so the -1 comes from the fact that we have a minus in front of the phi boundary. Yeah.
So if that coefficient was something else, it'd be -2.
Yeah. Yeah. Mm-hmm. Yeah. Remember, so when we're building these matrices, we're strictly taking the coefficients from the linear equations and then sticking them into the matrix. Right, yes. And so the question is, and so it's +1 for the inner ID for the left-hand side matrix. That's right. And so that +1 comes from the fact that this coefficient here is a 1. Yeah. I know it's a lot of moving parts right now, but I think, I did want to save a bit of time for the example. And so what you'll see that when we go through the whole example, it'll hopefully become a lot more clear how all these kind of parts kind of fit together.
Sorry, last question.
Yeah.
For my ID and the inner ID,
Mhm.
If we were evaluating on the right, would the +1, +2 change?
Yes, it would.
Would it be negative or just a different number?
It would be a different number. So remember on the right boundary, we come back up here. For the right boundary, the fixed value of I would be nx. And so my ID, instead of being +1, this would be plus nx instead.
Oh, so what we did before.
Exactly, right.
Okay, got it.
And then, but the inner neighbor is interesting. And so you wouldn't do nx +1, right? Because that would move you to the right. But then if we're on the right boundary, you want to move to the left to go inner. And so it would be nx -1. Yeah. Mm-hmm. Okay. Actually, one more small point before we do the example. And so let me draw the domain just one more time. Okay. And so we know that all the nodes on each boundary are going to have the same value, right? And so that kind of begs the question. There are some nodes in here where it's possible to have more than one boundary condition being applied, right? We have all the corner nodes, okay? So what about them? Right? And so if we have a different boundary condition on, say, the top face and a different boundary condition on the right face, right edges, then what do we do with the top right corner, right? And so do we take the boundary condition on the top face or do we take the one on the bottom? Do we have to change it so that it's compatible, or do we have to kind of make it halfway in between? It's a fair question. And so the nice thing about this is that we actually don't even care. And so the corner nodes can be whatever they want. and they actually don't affect our solution at all. Okay. Okay. And so why is that, right? Why don't they affect our solution? So remember, when we apply our finite difference equations to our interior nodes, we use the 5-point stencil, right? And so let's say that we're doing the finite difference equations for this one. Then all the nodes that are involved in its equation are something like that, right? Okay. In other words, it doesn't incorporate the corner nodes. Meanwhile, the nodes that actually do border the corners, right? So these two right here in blue, they don't rely on the corner node either. And so the blue ones, remember, we're applying just a boundary condition there, okay? And no matter if it's a Dirichlet boundary condition or if it's a Neumann one, the blue nodes here, they're not gonna, they don't take in the corner value at all, okay? And so we don't worry about the corner node. And so in other words, they never, they never become incorporated into our equation, okay?
Question.
Mhm.
So if we were to do a simulation on the heat transfer,
Yep.
would we see that the heat transfers on those blue nodes kind of dissipate to that corner node and we basically, so that corner node, is it dependent on the heat transfer on those two blue nodes, or would we see like a 0 degree Kelvin on that corner node, if that makes sense?
Yeah. So the by default, it's going to have a 0 value because we're basically just not going to solve for it. But just for visualization purposes, usually what people do is that they just make the corner node just have the same value as just the nearest one, and so either this one or that one. And so whatever you solve it to be, then you just have the corner node take that same value, just so that it kind of makes a nice picture. Yeah. And most of the time, especially if you're running Matlab, this grid here is extremely coarse, and so this is like you can play tic-tac-toe on this. But most of the time, you're going to make a grid that's a lot finer, right? And so the grid spacing is a lot closer. And so if you take the nearest value, then that's basically the same point. So.
Okay.
Mhm. All right. Any final questions where we do an example?
Yeah. Would you just mind going over the left-hand side matrix again?
Oh yeah. What about the left-hand side matrix?
Like it's just throwing me off the -1 and the 1 in terms of like. Because the way I'm kind of like interpreting the negative is the left side or right side. It's kind of confusing.
Yeah. So the signs and the values of what we put in the left-hand side matrix, they only really just depend on these equations, right? Because remember, the matrix that we're building is a linear system of equations. And so even though visually you might see something that looks like this, right? Right. And so it's just a ton of different values. Each row in this matrix kind of represents a different algebraic equation, right? And so this might be like phi1 is equal to 7, right? And this next row would be like phi1 minus phi2, 2 phi2 plus phi3 is equal to q or something like that, right? And so each row here is an equation. Okay? And so whenever you see a negative number, all that means is that the coefficient for that value is just a negative number. And so it doesn't mean sign or anything like that. The negatives just come out just kind of naturally from our finite difference applications.
Okay.
Yeah.
Okay, thanks.
Mm-hmm. Okay. Any other questions? Okay. All right. So let's go ahead and do an example. And so this will be a full example. So we'll take it kind of from the top all the way to the bottom. Okay. All right. And so let's consider the following domain. And so we're going to solve the 2D diffusion equation. Or let me give you the equation first. So solve the following equation. Okay. And so our equation will be partial squared phi partial x squared plus partial squared phi partial y squared is equal to 3xy. Okay. And so here we have a diffusion equation with a source term, okay? Which, you know, for all intents and purposes is, we'll say it's really difficult to solve by hand, okay? Okay, and we're going to solve it on the following domain. So here's our square domain. Okay, we'll say the length of each side. So Lx here will be 1.5. Let's just say meters, okay? Right, so the length of the domain in the y direction will also say is 1.5, and so we have a perfectly square domain, okay? And we're going to have the following boundary conditions, and so we're going to have phi is equal to 50, so we have a Dirichlet boundary on the left face. We have phi is equal to 25 on the right face. We have a Neumann boundary condition on the right face, partial n is equal to 0. And then on the top face, we have another Neumann condition, partial n is equal to 10. Okay. Okay. And so there's our domain, there's our equation, there's our boundary conditions. And so we're going to write the code to solve this. Okay. So let me do a couple calculations first. And then we'll go ahead and jump into Matlab. And so if you don't have Matlab open yet, I would suggest you open it now, just so that you can kind of help. And this code here, you know, just like you know, the first part of the homework, you know, this code here can be adapted to do the homework problems as well. Okay. Okay. And so right. And so when, you know, remember whenever we do any finite difference equations or finite difference solutions, we have to discretize both. Discretize the domain and the equation, okay? Okay. And so let's start with the domain first, okay? Okay, and so for the domain, I'm going to go ahead and break this up into 16 nodes. Okay. And so here this will be node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. I'm not controlling that. Okay. And so in this simple discretization here, we can see that we have an nx is equal to 4, right? Because we have 4 nodes going in the x direction. And we also have an ny is equal to 4 as well. Okay, so 4 nodes in the x, 4 nodes in the y, perfectly symmetric. Okay. Okay, and so that's the domain, right? I'm gonna do it simply here, just so that you know, I want to write out a couple of equations by hand, just so that you can kind of see. Okay. Now let's discretize the equation. All right, so let's go back up to our equation here. And so we have 2 derivatives. And so I'm going to break up both of them, or I'm going to discretize both of them using finite differences. So let's start with partial squared phi partial x squared. Okay, and so this is going to be phi I plus 1 comma j minus 2 phi I comma j plus phi minus 1 comma j. And this is all over delta x squared. Right, plus we're going to have partial squared phi partial y squared. So it's going to be phi I j plus 1 minus 2 phi I comma j plus phi I j minus 1. Okay. All divided by delta y squared. Okay. And so this is going to be equal to In this case, we have a source term. And so our source term is just going to be simply 3. Okay, xi, yj. Okay. All right, and so we're going to assume that we have a uniform grid spacing, which we do in this case, because we have the same lengths of the domain on both sides, and we have the same number of nodes on each side. Okay, and so I'm going to use this to simplify our equation. Okay. And so if we simplify, what we get is phi I plus 1 comma j plus phi I minus 1 comma j plus phi I comma j plus 1 plus phi I j minus 1 minus 4 phi I comma j. Okay, I move the delta square to the other side of the equation, and so we have 3xi yj delta squared. Okay. And so this right here, this is our finite difference equation for this problem that we can apply to the interior nodes. Okay. All right. So let me do this actually for a few of them, just so that you can kind of see how it's applied. Okay. And I'll show you kind of the pseudocode that kind of goes along with it. Okay. And so let's apply it to node. Let's just say node 10, because we've done node 7 before. Okay. And so for node 10, we know that I is equal to 2, right? And j is equal to 3. Okay. Okay. And remember, the reason we use ij notation here is so that we can kind of easily see which neighbors that we're looking at. And so we know that when the I is I plus 1, we know that this is the right neighbor. Okay. I minus 1 is the left neighbor. Okay. J plus 1 is the top neighbor. J minus 1 is the bottom neighbor. Okay. And then I comma j, of course, is the node in question. Okay. Okay, and so if we apply this to the equation, okay, and so for node 10, first we're going to need the right neighbor of node 10, and so the neighbor to the right of node 10 is 11. Okay, so we're going to have phi 11. Okay, then we need the left neighbor of node 10, which is phi 9. Okay. Then we're going to take the top neighbor, and so the top neighbor for phi 10 is phi 14. Then we need the bottom neighbor. The bottom neighbor for node 10 is phi 6. Okay. Then we have 4 times phi I comma j, and so that's going to be phi 10. Okay. Okay. And then in the right-hand side vector, we're going to have 3 times x2, where x2 is the x coordinate for when I is equal to 2, times y3, which is the y coordinate when j is equal to 3. And then we multiply by delta squared. Okay. All right. And so I'm going to show you how to apply these coefficients actually to the matrix, right? Because remember, each row in the matrix here represents a different algebraic equation. Okay. And so basically, we need to insert this equation here into the matrix. Okay. And so that means we're going to apply the coefficients. Okay. Specifically, since this is node 10 with an ID number of 10, the row that we're going to put this on in the matrix is the 10th row. Okay. This is not how you would actually apply in the code. And so in the code, you would actually use variables. But I'm going to put in the hard numbers for this one just so that you can get an idea of, what we're plugging in the loop. Okay. All right, question. So why did we pick node 10? I felt like Ben 10, I guess today. It was semi-random. Yeah, I wanted to pick an interior node, and I almost picked 7, but we did 7 last time, and so I thought we'd do 10 today. Okay. And so we're gonna need to make 5 specifications to the left-hand side matrix, and so we because we have 5 coefficients here. And so let me go ahead and write those out. Okay. And so for all of these assignments, our first entry is 10, because remember, we're making these coefficients on the 10th row of the matrix. Okay. So let's start with the diagonal entry. So let's do 10, 10, okay? And so 10, 10 is going to be the coefficient in front of phi 10 in the previous equation, okay? And so from the previous equation, you can see the coefficient there is -4, right? So we're going to have left-hand side matrix at 10, 10 is equal to -4, okay? Then we're going to go left to right. And so the next one is going to be phi 11. And so we're going to put left-hand side matrix at 10, 11. The coefficient in front of that is 1. Okay. Next, we have 10, 9. The coefficient in front of that is 1 as well. Okay. Next, we have 10, 14. This is also 1. And then we have 10, 6, which is also 1, just like that. Okay. All right. And so again, when we actually go to write the code, we're not going to hard code in the values of the indices like this. This is going to exist inside a loop, and so we're going to use our loop variables to actually assign these things. But I thought I'd do this just to kind of illustrate, when we say we're building this matrix, we're literally just putting the coefficients of our equations into the matrix to the right spots. Okay. All right. Any questions on this before we open up MATLAB? Okay. Okay. So I'm gonna go ahead and switch. Let me go ahead and switch to my computer screen here. Okay. All right, good. Whoa. Someone had even worse eyesight than I need. Okay. I'll change that a bit. Okay. So I have starter code for you. So we're not going to write the code from scratch just because the 2D code is a little bit more involved than the 1D one. And so if you go to our course website, and you go to week 4. Okay. So if you go to week 4, you can see here, first thing you should see are the solutions to homework 1. And so you can check those out when we get a chance. But the one I want you to download today is this EGME 417 2D diffusion finite difference starter. Okay. Oh, it actually displays it. Okay, so let me go ahead and download this. Okay. And I'm going to open it up in MATLAB. Let me change the font here because this is a little bit too much for me. Once. Yeah, okay, that's crazy. Let's do 14. I think that worked, right? No. Okay. Bring this to a new window. Okay. All right. And so if you open up the starter code, you should see this. Okay. Let me go ahead and switch this up here. Okay. All right, so I've written most of the skeleton for you, and I've even labeled out, what you need to do in each section. And so we're gonna go through each section of this starter code. All right, and so let's go ahead and start at the top. And so at the very top, you can see here that I have a section here where we're going to define variables, right? And so this top section here, we're going to determine, we're going to write down all the different main variables of our problem. Okay, so I already have some of these for you. So you can see here that I have nx and ny, which is the number of nodes in each direction. Okay. Another thing that you're going to need is you're going to need Lx, right? So Lx, remember, is the length of the domain in the x direction. Okay, and so for this one, it's 1.5. Next, we have Ly, and Ly is also 1.5. Okay. Right, so we have nx, ny, lx, ly. Okay. All right, so the next thing we're going to do is we're going to define the grid spacing. Okay. And so you can have separate variables for this, although we're going to assume that they're the same. Right, and so remember, the grid spacing is the amount of physical space in between each node in our grid. Okay, and so remember, the way that we compute this is we do Lx. Well, in this case, I'm going to do Lx, and we're going to divide it by the number of nodes in that direction minus 1. Okay, and so we have dx here is equal to Lx divided by nx minus 1. And so this right here is the grid spacing in the x direction. And then we're going to do the same thing for dy. So dy here is going to be Ly divided by ny minus 1. Okay.
Increase in the font size?
Oh, yeah. Sure.
Unless you want to like stream it to every computer.
That is true. That is true. Let's try 18. Is that a bit better?
Yeah.
Okay, good. All right, so now we have dx, dy, and so those are the grid spacings in the x and y direction. Okay. Last thing we need to do is we need to preload or create space for the left-hand side matrix and the right-hand side vector. Okay. So this is, I'll make one called left-hand side matrix. Okay. Remember the way that we do this, because most of the entries are going to be 0, is we're going to use the zeros function. Okay. And the size of this matrix is going to be n tot by n tot, where n tot is the total number of nodes, or total number of grid points in our mesh. And the right-hand side vector is going to be, the size of that's going to be n tot by 1. Okay. This is the left-hand side matrix of P coefficients. Okay. Here's the right-hand side force. Boundary conditions. Okay. Okay. All right, so this is just all bookkeeping, and so these are all just kind of main. I call them kind of like main parameters for the problem, and we're going to keep referring to these as we go throughout the code. Okay, and so that's it for section 1. And so are there any questions on any of the variables we defined here? Okay, so next thing we're going to do is we're going to populate the left-hand side matrix for all the interior nodes. Okay. And so we're basically going to apply the same thing that we just did for node 10, but we're going to apply it for all the interior nodes. Okay. Okay. And so since we're visiting potentially a lot of interior nodes, and in fact, we don't know how many interior nodes we're going to visit. Remember, the best way to do these kinds of tasks in programming is to write a loop. Okay. And so loop lets us repeat a section of code as many times as we want. And depending on the bounds of the loop, do this as many times as we want. Okay. And so I want to make one thing kind of clear on this one. And so remember that we're only applying these for the interior nodes. Okay. Because for our interior nodes, remember we have our 5-point stencil. And so that's going to only apply if we have neighbors on all 4 sides of us. Okay. And so we can't apply this finite difference equation on the boundary nodes because we don't have enough neighbors for them. And so for the boundary nodes, we're going to apply our boundary conditions to them. And so that's sections 4, 5, 6, and 7. Okay. And so to only visit the interior nodes, well, first of all, if you want to visit all the nodes, it would look something like this, right? And so we have 4I goes from 1 to nx. And so that would loop over all the x ones, and then you would have a nested for loop that looks like this, right? Okay. And so these 2 loops right here, 4i's equal from 1 to nx, and 4j is equal to 1 to ny. This is going to visit all the nodes in the both the x and y directions in our grid. Okay. But remember, we're only applying this for the interior nodes, right? And so we don't want to start all the way to the left and go all the way to the right. Okay? We actually want to start 1 over from that. Okay? And so instead of 1, start at the very left, we're going to start 1 over, so that's 2. And instead of nx, we're going to do nx minus 1, right? And so we're going to stop 1 short of the final one. Okay? Same thing for j. Okay. Right. Does that make sense about why we changed the loop bound there to only be 2 to n minus 1 instead of 1 to n? Okay. All right. So the next thing that we need to do is inside this loop, remember, we want to assign the proper coefficients for the left-hand side matrix, right? So all the coefficients in front of the phi terms, we're going to do that. We're going to do that right here. Okay. So in other words, we're going to have left-hand side matrix. We're going to have 5 entries here, right? So left-hand side matrix, left-hand side matrix, left-hand side matrix, left-hand side matrix. Right? Because our general finite difference equation for this has five entries, right? So we have the 4 neighbors, and we also have the node itself. And I need one more. Okay. And so that's what we're going to do in that section. But in order to specify these in the correct row, remember what we need to do is we need to compute the ID numbers for all of these, right? Right, because the ID numbers are going to tell us what row in the what rows and columns in the matrix that we need to assign these to. And so we're going to need to compute 5 ID numbers here. Okay, so we're going to need to compute my ID. We're going to need to compute, which is the ID number for node I and j. Okay. We're going to need to compute the ID number for the left neighbor. Okay, so we'll call that left ID. We're going to need to compute the ID number for the right node, so that's right ID. Then we're going to compute the ID number for the top neighbor, which is top ID. Okay. And then finally, we need to compute the ID number for the bottom neighbor. Okay, so let's start with my ID first, because this is the simplest one. So this is kind of just a direct application of the equation that we use. Okay. So remember, the ID equation that we have is going to be j minus 1 multiplied by nx plus I. Right? And we can use I and j directly into this equation because those are going to be our loop variables, right? And so that's why we put I and j, because we know I and j is going to visit every single possible I and j on the interior. Okay. And so now that we have the equation for my ID, let's go ahead and write the equation for the left ID, right? And so if we're going one left of the current node, that means the I value of the left neighbor is 1 less the I value of this current node. Okay. Okay. And so instead of plus I, we're going to do plus I minus 1. And then same thing for the right neighbor. So for the right neighbor, we're going to have j minus 1 times nx plus I. But in this case, since we're moving 1 to the right, then the I coordinate for that node is going to be I plus 1. Okay, and so now let's go ahead and write the ID numbers for the top node. And so if we are looking at our top neighbor, that means our j is 1 plus what we are, right? And so instead of j minus 1, I have j minus 1 plus 1, which you can cancel it out, and so I can have just j. But I'm going to leave it as minus 1 plus 1 just to make it illustrative. And the I value is the same for the for this for our top neighbor. Okay. And then for our bottom for our bottom ID, our bottom neighbor, then we're going to do j minus 1 minus 1 because our bottom neighbor has 1 less j than we do. Okay. So any questions on how we computed the ID numbers for all these guys?
Since nx and ny are equal, then for the top and bottom, it doesn't matter if we use nx or ny.
So for in this case, yeah, since they're equal, then you can interchange them. But it's good practice to kind of keep them separate, so that if you decide that I feel like changing nx to 40, then the rest of your code is going to automatically update. But yeah, in this case, since they're the same, you can interchange them. Yeah. Okay. All right. So now let's go ahead and write in the coefficients. Okay. So remember, everything is going to be in the myID row. And so I'm going to go ahead and write this for every single row here. Okay. And so all of them are going to have myID for the row. Next thing that we're going to do here is we're going to set the coefficient, right? And so in the myID slot, so this is the corner slot, remember, or the diagonal slot. Remember, we have a -4 there. And for all the other ones, we have a 1. Okay. Right. So this is basically, exactly the same as our, as a calculation we just did. But instead of putting in the hard ID numbers, I just put in the variable representations instead. All right. Any questions on this? Okay. All right. So that takes care of all the coefficients in the left-hand side matrix for the interior nodes. Okay. And so the next thing that we're going to do is we're going to apply the forcing function to all the nodes in the mesh. Okay. And so remember, our forcing function was 3 times x times y. Okay. And so we need to apply this to all the nodes in the mesh. And so we're going to use the same loop structure as above, but since this is applying to all the nodes, right? And so the forcing function doesn't care if we have any neighbors or not. And so we're going to apply this to all of them. And so we're going to do 4i is equal to 1 to nx, and 4j is equal to 1 to ny. Okay. And we're going to need to make a contribution to the right-hand side vector. Okay. Okay. And so that contribution, of course, is going to be, we're going to summon the right-hand side vector. Okay. Right. And so we're going to make a change to that vector there. Right. And the entry that we're going to put in there is going to depend on myID, right? And so just like we did for up here, and actually we can just copy and paste the exact same formula. Okay. Since we're looping over I and j, right, we can compute the ID number for this node using the same formula. Okay. Okay, and then we're going to input directly our forcing function. Okay. And so we have 3 times x, the x position of this node, times the y position of this node. Okay. And then we're going to multiply this by dx times dx. Okay. Because if you remember from our finite difference equation, we had that delta squared come out because of its because it came from the finite difference approximation of the other terms. Okay. Okay. Any questions on how we did this here?
One more time, would you mind explaining the my ID one?
Yeah. So the my ID. Remember, whenever we're making any changes to the left-hand side matrix or the right-hand side vector, we want to make sure that we apply it on the appropriate row and the appropriate column. And so this my ID basically says that, if we're at the node for I comma j, then this tells us exactly what ID number is. Yeah. Yeah. All right. But there's one problem with this. And so the problem is that, I use these variables x pos and y pos, right? And of course, they're supposed to represent the x position and y position of this node, but we haven't actually computed them yet, okay? And so we actually need to compute what x pos is inside this loop, as well as y pos, okay? Okay. And so these are going to be the physical x and y coordinates of the I and j node, okay? And so, just because we're running a bit short on time, and I want to make sure I show you at least one of the boundary loops, I'm just going to write this in for you, okay? Because this is part of the homework, and so I want to make sure I cover everything. Okay. And so the way that we compute the x position and the y position is we take the I and j coordinates. Oh, sorry, not nx. You take the I and j coordinates, you subtract 1, and then you multiply that by the grid spacing. And so that's going to give you the physical coordinates of the x and y, x and y coordinates for that particular node. Okay. Right. And so now that we define x position and y position, we can go ahead and plug it back into this equation, and we'll have set our, our equation just fine. Okay. Any questions on that? Okay. All right. And so the next thing we're going to do is we need to have 4 different loops here for the boundary conditions. Okay. And so we're going to have 1 loop for the left boundary, 1 loop for the top boundary, 1 for the right, and 1 for the bottom. Okay. And inside these comments here, I've told you which nodes are fixed. Okay. All right. So let's do the left boundary just really quickly first. Okay. And actually, we already kind of wrote the code for this already in our notes. Okay. And so for the left boundary, okay, we're going to loop from j is equal to from 1 to ny. Okay, because remember, we're on the left boundary, our j is varying, but our I is fixed. Okay, and if you look back at our example problem, you'll know that for the left boundary, we have an essential boundary condition, or in other words, for essential is a Dirichlet boundary condition. Okay? And so to apply this, we have to compute the ID numbers. We have my ID is going to be almost the same as before. And so we have j minus 1 multiplied by nx. Okay. Normally, we would have plus I here because that's our ID number equation. But since we're on the left boundary, we know that the I value is fixed and its fixed value is 1. Okay. And so I directly plugged in I is equal to 1 into this my ID equation, just to illustrate that. Okay. Next thing we need to do is we need to specify the left-hand side matrix. Okay, so we have left-hand side matrix at my ID. Okay. And so the diagonal entry is 1, and the right-hand side vector, my ID, we set this to our Dirichlet value. So our Dirichlet value in this case is 50. Okay. Right. And so you're going to repeat that same logic for the boundary conditions on each of the different other faces. Okay. And so I did want to show you the result, and so I do have the final result here uploaded onto Canvas, and so I wish we had time to go over it all. But if you go to Canvas and you make this go away, okay, you go to Files, you go to Code. Okay, so I've actually uploaded all the codes here for the semester, and so we're gonna go through all of these this semester. Okay, so I have this one right here called 2D diffusion finite difference, and so this is kind of the finalized version of the code that we're writing just now. Okay, and so I just want to show you the result. Okay, and so this is for a grid that's NX 50 and 50. Okay. It's taking a bit of time. It's taking sweet old time. Okay, and you can see the result looks something like this, right? And so you know, now our results are going to be these color contour plots where the colors represent our function values. Okay. Right. And so if you finish the rest of the code, then you know, your result is going to look basically something like this. Okay. All right. Any final questions on this before we wrap it up? Okay.
For that plot.
Yeah, I'm sorry we didn't get a chance to go through, you know, we didn't get a chance to go through the code that carefully. But I did want to show you where the final result was so that, you know, so that you can start using it for your homework. Okay. And so kind of take what we talked about today and then, you know, reference it with the solution here. Okay. Pay special attention to how the Neumann boundary conditions are applied, because those are a little bit tricky. But we did write the pseudocode for that in the class. Okay. Okay. And so I'm going to go ahead and answer a couple questions at the end here. And so if you want to stick around for that, you can. But if not, then have a great long weekend, everyone. Remember, we don't have class on Monday, and so you know, don't come here, don't go on Zoom. I won't be here, but I will hold office hours on Monday, and so I will hold virtual office hours. And so if you want to talk about the homeworks or anything, you know, just log on to Zoom and we can chat. Okay. Okay. And so I'm going to answer a couple of the last Zoom questions. And if you have any questions here, you know, you can go ahead and ask. But if not, thank you, everyone, and I'll see you next week. Okay. So first question, can I explain why the x plus and y plus have a -1? Yeah, so the x plus, y plus, the main reason they have a -1 is just to make sure that the origin has a coordinate of 0, has x coordinate and y coordinate of 0, right? Because the I here starting at 1 and the j starting at 1, right? And so when I and j is equal to 1, in other words, we are at the origin. Okay. We want this to have a physical coordinate of 0, 0. And so we have the -1 there to make sure that that happens, basically. Yeah. All right, Chris, your question. So what is the colors represent? So the colors represent the function value. And so in the 1D case, remember when we solve for the function value, we could see it in terms of the height of the plot. You know, when you're in 2D space, you know, we don't have any 3D graphs. I mean, you can do a 3D graph, but it's actually kind of a pain to look at. And so instead of using like height to represent function value, we use colors instead. Yeah. And so you can see the color scale here. So the bright yellow will be 50 and the bright blue will be 25.
So the brighter it is, that shows what boundary we're focusing on.
So the colors just, so, you know, this is our 2D domain, right? And so this is our square domain that we were working on before. And so the colors just represent, you know, if you can think of it as like temperature. And so the colors represent how hot that temperature is at those locations. And so, you know, at this location, then, you know, we have a temperature of 50 and down here we have a temperature of 25.
Thanks, Sean. Have a good weekend.
Thanks, Eddie. You too. Yeah, think of it like ANSYS, right? And so ANSYS, you know, we viewed our results in the same way. So our results were viewed as like a color contour plot. This is exactly the same thing.
Okay, that makes sense. All righty, cool. Thanks.
Yep. Thanks, guys. Have a good weekend.
All right, thanks again, Dr. Tran. Hope you enjoy your weekend.
Thanks, you too, Chris.
So physically, that's just a kind of like for example, the front screen of your computer,
Yep,
is that what physically the square would represent?
Yep. Yeah, and so we have a pure square domain here. And so remember the length of each side of the domain is 1.5 meters. And so you can think of like the x coordinate at this point down here would be like 1.5. And this would be like 1.5, 1.5. Yeah. Yep. Mhm. Hmm?
With one cheeseburger.
It's a good deal.
All this information for a cheeseburger. Updated one dish.
Yeah.
Is it possible to change the colors or is it just on the default?
You can change the colors. Yeah, MATLAB has a lot of different options. Personally, I just keep the default, but if you search up just MATLAB plot colors, then you can see a ton of options there. Yeah, thanks guys. Hey.
Got some good news today.
What? Nice. With who?
With Boeing, the one.
Nice.
That was the one that I emailed you about.
Nice.
the reference, but
Congrats,
it
man.
wasn't like a required thing, so.
I told him
I
I
didn't
cut
put it on.
that hair.
But I was excited, so I wanted to. say it.
Nice. Congrats,
Yeah, I
man.
definitely gotta go get a haircut.
All right, Rebecca, any final questions? I have to teach another class, but I can answer one quick question. Okay, all right, I'm gonna sign off then.